Hello, everyone. Welcome to the APSCE webinar series. We have with us Professor Tiffany Barnes. Professor Tiffany Barnes is a distinguished professor of computer science at North Carolina State University and a distinguished member of the Association of Computing Machinery. She was the founding co-director of STARS Computing Corps, a broadening participation in computing alliance funded by the US National Science Foundation. Her internationally recognized research program focuses on transforming education with AI-driven learning games and technologies, and also on research supporting equity and broadening participation. Her current work spans intelligent tutoring system, teacher professional development, computational thinking, artificial intelligence curricula, and personalized learning technologies. All these have impacted thousands of K-12 students across the United States. In addition to these impressive accomplishments, Professor Barnes has played a pivotal leadership role in the education data mining community, helping shape research directions and nurturing collaboration across disciplines. Her commitment to mentoring emerging scholars and advancing data-driven educational innovations have made her an influential figure and a highly respected colleague in our field. We are especially delighted to welcome her today, as her mentorship and leadership have deeply shaped the trajectories of many emerging scholars in the field. Welcome, Professor Barnes. Over to you.
Thank you. Is there any other intro, or shall I get right into my slides?
Yeah, I can go ahead and write into the slides.
Thank you so much for the wonderful introduction. I'm really happy to be here, and thank you so much for the invitation. I'll share my slides and get started.
Sure.
Does that look good?
Yeah.
Great, thank you. Thanks again for inviting me. I'm very delighted to be here to talk with you all. And the title of my talk is Strategic Scaffolding, Data-Driven Design for Computational Problem Solving. And I'll give you a hint. After I wrote the talk, I decided to focus only on logic. So it's all going to be logic, but I teach logic within the discrete math class at North Carolina State University, where I work. And I'm happy to be giving you a talk from here. And all of my work has been on data-driven design for scaffolding problem solving for students. And these slides are available at this Go link, go.ncsu for North Carolina State University.edu/APSCE25. And I'll share these with the organizers so they can send them out to you as well. All right, so what is computational problem solving? The problem is that when students solve hard problems, they struggle to bridge the gap between the abstract and solving concrete problems. And many of us who teach computer science often think we're teaching concepts, and then when we look at the data about what students are doing when they're writing a program or doing a logic proof, we find out that what students are doing is they're learning the language that we taught them, or they're learning how to solve, how to apply the rules that we just taught them. So we might be thinking we're teaching data structures, and they're thinking that we're teaching Java, or we might be thinking we're teaching complex problem-solving strategies when they're thinking I'm trying to learn these logic rules, which is sort of humbling to me after 20 years of research trying to support logic proof learning. I'm still finding that most of the things that we do help students learn the rules rather than high-level problem solving. So this is an aspirational goal, is to help students, learn at a high level, learn these conceptual things. But by doing that, by actually applying learning analytics and educational data mining to student problem solving data, and then learning what's working, and then applying that to generate content or direct students in learning environments to what should they do next, what problem should they solve, or maybe what scaffolding should I give them, like a hint or a progress indicator and that sort of stuff. So one of the first ideas of an intervention is, an ancient one. I feel like, as a person who went to school many, many years ago, textbooks were like the first, instructional intervention that didn't involve having another person next to you, right? And the thing you learn the most from in a textbook is a worked example, right? Like, I've got to do these problems. Let me think about how to do it. Let me read how this problem was done by someone else. So, and they have been extensively studied, and they can save students time and without reducing their learning. So many studies have shown this, and there's lots of studies of interweaving worked examples with problem solving. There's lots of different research. And in fact, some of the research I do with Dr. Minchi, who's amazing, we have been applying reinforcement learning to decide when to give students worked examples. But we're also finding that, students can skip them, right? So they just, in the context of a problem solving environments, many times students become passive when they see a worked example. It's like, oh, I don't have to type anything. Let me click next. And I'm guilty of this too, right? I download a new app and it's like, let me show you where to click. I'm like, no, I want to get to the thing that I'm trying to do. And then I get stuck right after I get started going, I don't actually know how to do anything in this environment. So, it's human to sort of skip through, ignore the very valuable things that people have structured for us. But that means we've got to rescue people later. It's our job to teach people and help them with problem solving. So we want to figure out how can we use data to help students in the middle of problem solving. So when students are doing unstructured problem solving, like writing a program or solving a logic proof, this can give some high cognitive demands on students. So one of the, worked examples have this problem that students don't read them. If they don't engage in them, then they may not be working. But if they're, totally going to solving a problem from scratch, that's also really hard. And they might get stuck from sort of blank page syndrome. Like, what do I do next? So Parsons problems have emerged as a promising scaffold for teaching structured problem solving, like in programming. I hope that many of you have heard of that. If you haven't, it's sort of like, think of taking a program and printing it out and cutting it into pieces and asking someone to reorganize those pieces. That's sort of the original idea for Parsons problems. And they have research on Parsons problems has advanced quite a bit for programming with adaptive Parsons problems that's led by Barb Erickson and Carl Magyar-Haynes. Really great work on adaptive Parsons problems, looking at what do students need and how can they learn from a Parsons problem. But sort of when they were invented, people were like, wow, we've solved a lot of introductory programming problems by letting students rearrange programming puzzles. And what we're finding now is maybe they need some more scaffolding even to do Parsons problems. So the idea there is you don't have a blank page, you've got pieces to rearrange, and just thinking about reading those pieces and rearranging them, they can help you learn a lot without you having to start from a blank problem. And so when I was inspired by that a few years ago and wanted to take those Parsons problems idea and put them in logic, in our logic proof tutor. So I'm going to tell you about what we did with that. My student Preya Shabrina, some results that she got, and then they weren't awesome. And so then I'd like to tell you our latest results on Parsons problems and where we have gotten with that. And so I'm going to kind of give you slides from two different talks, one from 2023, one from 2025, and we'll see like where have we gone with Parsons problems in logic. All right, so the basic approach that's underneath everything I'm going to talk about tonight is that within a problem-solving learning environment like programming or logic, and we're only going to talk about logic for the rest of the evening, we log student steps, like we record, like what did they enter, what did they try in a problem-solving step, what did they click on, did they make a mistake, was it logically correct? So within our logic tutor, was it logically correct or incorrect? If it's incorrect, it erases, gives them a feedback and erases it. If it doesn't, it appears on the screen as the next step. And the students have to give a justification for each step. And I'll show you a screenshot of our environment in a minute. The basic idea underneath all of this is that at the end of every step, we've got a snapshot of that problem-solving state. So I want you to have that in your mind, that even if it was something on paper, you could have the same idea for a paper-based problem-solving approach, take a snapshot of what was done, and a step is the different, I added a new step in my problem solving, or I added a new programming line. Like that's what I would consider a step. Like I have done a step in the problem solving. I've added a new command, or I've added a new statement in my logic. And then we build what we have called an interaction network, which is basically a graph that links all of the consecutive snapshots of problem solving steps. And underneath all of my research is thinking of that graph as a Markov decision process and the observed frequencies between steps as the transition probabilities for a Markov decision process. And if you don't understand that, you don't need to. It's just the underneath the hood, sort of how do our hints work and that sort of thing. But basically, once we have that interaction network, we apply learning analytics to that data, and educational data mining techniques to that to build models of problem solving. And then here, and I'll tell you more about this, we built sub-goals for problems that we discovered from student data, solving logic proofs. We verified that they were the same sub-goals that experts would find, and we used them to build Parsons problems. So we'll talk a little bit more about that. All right, so this is the title of the paper that was presented at EDM 2023 that I'll present again tonight. And this is a really long title, but it's basically like, can we teach students to solve logic problems with a new design for Parsons problems translated from programming into logic? All right, so like I said, Parsons problems, like, take the steps of a problem, cut them all up, and they've got to put them in order. So this is like the expert view. Like, I know this is step one, this is step two, but the students don't know that. This is just, there's some content on the screen. They've got to reorganize it. So they have like, what's the problem statement? What are they given? They need to accomplish the goal. What's the order to do these to get that goal? All right, and so the idea that we wanted to do is we wanted to move students to becoming more expert. And if you've heard of, there's one phrase when we talk about expert versus novice problem solving. An expert will do things in chunks, right? They'll think of like, oh, I have this sub goal, and like, tying my shoes. I don't think about all the steps I do in tying my shoes. I think, okay, make a loop, wrap the loop around, pull the other loop through. But there's a lot of small steps going on underneath. But as you get more expert with something, you think in chunks, like you group up the steps that you're doing, and each of those groups of steps have a sub goal. So that was our overarching idea when we tried to take the steps in logic problems and group them together into small steps that were done, frequently together. And then the result of those steps, we called those sub-goals. So we could learn the data from student data. We could learn these groups of steps that were done together and find out what the problem sub-goals were. So that's the overarching thing here. So each of these are chunks, like groups of these, like, steps 1 and 2 are the first sub-goal, steps 3, 4, and 5 are the second sub-goal, and sub-goal 3 is steps 6 and 7. And these are actually seen as working backwards from the goal, because another thing that experts do is they frequently work backwards from the goal, right? They look at what they're trying to derive, and they think, well, what could I do that would lead to that? And they kind of work backwards while they're also looking at the given. So even if it appears that they're working forwards, many times they are setting sub-goals that are equivalent to working backwards from a goal. All right, so we built this Parsons problems. I'll show you a picture of it. We wanted to see, did they make a difference on performance and learning gain? Did they have any difficulties with these Parsons problems, and how did they do? And then we might skip some of that so we can get to 2025 results. All right, so here's a picture of our deep thought logic proof tutor. On the left here, we have givens, so they're in purple. So these are logic statements like not the quantity T and L is one of them. Number 2 is not T implies not N. And we have not the quantity E or T as another given. This green statement is a student-derived step. In the middle here, we have rules that students can apply. This first one's called modus ponens. It's, I call it the if it rains, you're going to get wet rule. And it says you have an implication, like if it's raining, you're getting wet. And then I tell you that I know it's raining, then you know that you're getting wet. That's the modus ponens rule. So students can click on these to derive new statements. So they'll click on a parent, say, for example, this number 3, they clicked on De Morgan's because this is a apply a not across an operator. That's the De Morgan's rule. They click on that and they can derive this step. And their overarching goal is to derive the conclusion, which is down here. It has a question mark above it to indicate that this is not proved yet. Also in the environment, students can click on this and work backwards. So instead of working forwards, like from the top down, they can also work from the bottom up, working backwards. So they can click on this, click a rule, and specify how this might have been done. At the bottom here, we have a hint, tells the students try to derive not T working forwards. So that is the next thing to do after this. So this is an and statement. We could simplify this using the simp rule and get not T. That's the next step. So clicking on this and simp would allow them to meet this goal. There's a couple of other things at the bottom, but they're not important. All right, so let's first talk about how do we figure out what the data-driven sub-goals were. So we took the historical student solutions, we turned them into interaction networks, like I mentioned to you, and then we applied Gervon-Newman edge betweenness to them to make what we called approach maps. So basically a graph-based mining technique that breaks up our interaction networks into regions of steps that were done together. And then we use 3 rules to extract some subgoals from these maps. So we started with interactions, we get an interaction network, we cluster it, and we make an approach map. By the way, this is just details on an interaction, and this is an interaction is an atomic operation that results in the derivation or deletion of a single proposition. So it's a step in a problem solving. These are lists of all the statements on the screen. So these are like a list of givens, and then if a new statement's added at the end. So if you notice, everything here is the same, except for this is the new statement that was added on the end. It's not important that you understand those. So the idea is that the new states are all appending new information. So any kind of problem solving that you've got, you can just keep a list of everything that's been derived, and when a student derives a new thing, you just append it on the end. All right, so this is a picture of a interaction network. They look like spaghetti, and you don't need to be able to read this, but the whole point is that, they start at the beginning, and then anything green at the bottom, these are super tiny, but the green ones are student finish the problem. So each level of this is how many steps did it take. So some students took a lot of steps. Some students, finished relatively early up here. And then we cluster it. And if you again, you don't need to be able to read these, but you can see that there's a few colors, right? So that's what these are. The colors are clusters, and these are regions, what we call approaches. And the path that a student takes to get to their solution, like people down here, let's say I'm over here, some of them came from here. So this is a region in my approach map. This is a region. So in order to get here, I would have had to come through this purple one, and probably from up here. So the approach is sort of following all of these regions to get down to where a student put together. So then we basically collapse each of these colors into a node and make a higher level, like a hierarchical graph of this. And sort of see how do people traverse between the colors on this other graph. And then we remove any redundant paths, and we label the edges with how did people transition, like what are the labels on these edges between colors. So if I go between this purple color and this sort of dark blue color, what was the transition that we did? Like what rule did we apply? These are rule labels, like modus ponens, or these are logic rules. All right, and then these are just those lists of interactions that the students have. So these are all of the steps that students have done. So now we've got this high level map of how students solve the problem. All right, and then we made some rules, like how do we figure out which ones of these things are subgoals, right? So remember that the idea of the chunks were that small groups of steps that were done together, and what was the reason, like why they did those things. So how do we get that from data? So this is a region here. So rule number 1 is we have nodes. The first node of a region where multiple regions merge. So these 2 regions merged. So this one is a subgoal, right? So both students who did this and students who did this were all trying to get this because everybody did do that next. So the evidence is there in the data. All right. So this is the same graph. We have a second rule. The last node of a region that generates a fork. So this is a region that generates a fork right here. So this was already a subgoal, so we don't need to make this one a new subgoal. Rule 2, so this is a rule 2 rule, but remember, it was also a subgoal based on being a merge there, but it also generates new paths, so a split. So it is also a subgoal according to rule 2. This is a subgoal according to rule 2 because there's 2 split paths here. So you see some of these nodes only have one path, and that means they're not going to be subgoals. All right, and then rule 3 is if there's a chain of regions, like these are the regions, if there's a chain of them, the last derived step in each of these. So that's how we learned the subgoals for each of the regions. All right, and then we did decomposition of the problems into chunks. So everything that came in the region before that subgoal is listed. So all the chunks are basically, it's separated into non-overlapping regions of the graph. So the idea of a chunk is you can't have something in 2 different chunks. All right, so here is a picture of how we translated that back into the learning environment. So here's the givens again, and then every node the students have to derive is on the screen. But instead of all be totally cut apart, a finished problem in this environment, I'm sorry I didn't show you a picture of that, looks like basically all these orange question marks are gone and all the nodes are connected. So the thing that students have to do in this environment is they just need to figure out, like, these are all derived statements. So this one's a tricky one, but the rest of these are derived statements that the students, if they start it from blank, it would just not have any of the stuff in the middle, and it would just have the purple at the top and the bottom. All the nodes that they need to solve the problem have been added to the environment. And all they have to do is say, how does this lead, how does this chunk, so here's a chunk, how do the givens get to this chunk? How does this chunk get to that one? And how does this one get to that one? So basically they need to click on one or two nodes, click a rule, and have it derive one of these statements that's on the screen. So they're not deriving whole steps anymore. Now all they're doing is giving some reasons for why these steps were done. All right, so let me just talk through this one for a second. So here, in order to get this not O or L, looks like if I combine that, so these arrows mean if I take these two, this node and combine it with modus ponens, I'm going to get this. So I click this to tell the system that this is rule number one, like given number one actually is what goes here. So when I combine this statement and this statement, I will get that. So this chunk is, how do I combine this and this to get M and not N? That M and not N is a subgoal. And this one comes from step 2. So I have to click on this to say, oh, not O, and the addition rule will give me that. So again, you don't need to know the details, but the idea is that they're basically drawing arrows between the nodes to these. All right. Hold on, just need to adjust my view for a second. I'm going to thank Ashwin for being my very attentive audience. So you're really helping me out and making me feel like I'm not by myself in my house. So thank you so much for showing on your face that you're paying attention and enjoying. Maybe you're faking, but I really appreciate it. Okay, so here's our experiment design for checking this out. So within our tutor, we have 7 levels. So level 1's a pre-test, level 7's a post-test, and in the intervening, these are called the training levels, and the 4th problem in every training level is problem solving. They don't get to get any hints. They don't get to do Parsons problems. It's a kind of a post-test for that level. And every level has rules that the students are supposed to be learning. So the problems are, supposed to be increasing difficulty from the beginning to the end, and each level adds more rules. And then we'd had 3 conditions in this experiment where we had a control condition where the students were doing interleaved either problem solving or worked example for every problem. So the control group in every situation in level 2 here, and actually across all of these training levels, they were always doing problem solving or worked examples, like randomly selected. I think it's slightly less likely to get worked example. And then treatment 1 was they got these chunky Parsons problems, and instead of a worked example. So randomly selected, like, do you do a problem or do you do a chunky Parsons problem for every problem in these levels? And then the second training condition was some extra explanations were added to those chunks. So to the subgoals and what to do. All right. I'll give you a hint or a preview of the result. This one was terrible, and you probably already can tell that. Like, I wish I could do a poll for you guys, but basically, you probably looked at this and I had to explain it for too long, and you're probably like, I have no idea what to do with that. And a student who doesn't know their logic proof rules very well are also like, I don't know what to do with this. What are all these things on the screen? So, the cheating preview is that they really needed the explanations. So without explanations, we've totally trashed that. All right, so what happened? So we have a logic course where students have to do these problems, use this system, and we had about 50 students in each condition who finished. So these are our looking at how the students did. Remember, level 7 is our post-test, so that's over here. And we have our pre-test as level 1. And then these are the 4th problem in every level. These are the training problems. So this is our performance. So when we look at, let's see, what are the colors? Oh, the colors are here on the legend. All right, the control is this blue. Our graphs look very similar every semester. So they kind of, every level, remember, they have to learn a new rule. So they kind of go up and down. It doesn't look like a learning regression where they get faster or, it's up and down because they're learning new rules every level. And that's how that goes. So we actually see that, there's the treatment 2 with the explanations, chunky Parsons problems and explanations doesn't look all that different here. It's sort of like, up and down. But on the post-test, they do way better. So the chunky Parsons problems did help them. But you see also, but treatment one actually didn't. You see that actually performance went way down. It took them forever to figure out what the heck to do. And finally, when they did, it didn't help them that much. So I think it was distracting from their learning because they really didn't know what to do with that interface. So one lesson learned here, carefully design your interface so students actually know what to do. Otherwise, you can really damage their learning. All right. Okay, so this is a confusing graph, but this is a histogram of normalized learning gain, which is the post-test minus the pretest over the square root of 100 minus the pretest. So to normalize based on how much gain did students make according, divided by how much they could have made. And if you look on here, we have the experimental condition is in pink. And you can see that there's much better positive scores on there, and that the blue is the control, and we've got even some blue over here, and the yellow was the Chunky Parsons problem. So some people learned from them, but some people really didn't do well with the Chunky Parsons problems without explanations. With the explanations, so we've got our learning gains are looking better. The distribution of learning gains is better. All right, and then we tried to figure out, like, okay, what's going on with these Parsons problems? Why are they doing better at the end? Like the normalized learning gain is looking better, but the time was really not great. So what we found out is that in the first couple of levels, learning how to use these Chunky Parsons problems was really slowing them down. So we look with our explanation. So it took them some significant time in level 3, up level 2 and level 3, to actually learn how to do those Chunky Parsons problems. But later that time went down. So they had learned how to do them, and then they were actually getting faster than the control, which is here, like doing problem solving. Worked examples, by the way, look, they're spending almost no time on those. They're not even reading those things, right? So the idea of the Parsons problems is get the students to do something active where they're doing more than reading. Like they've got to add some edges in this graph. So it took them a while to learn how to do it, but afterwards they got almost as quick as worked examples, but they actually have to do something. And they showed learning gains. All right, so I want to get to what do we do? So I'm going to skip over this. Y'all feel free to look at the slides of the paper. But we basically did a lot of analytics to really understand like what was going on with whether or not the students could learn from these. But overall, I can just tell you, most of the students didn't learn that much from this. We did find out that, what was this one? So we looked at sort of like what happened to low scores, medium scores, and high scores on the pretest, I think. Yes, based on the pretest. Just to see like who was this impacting more than others. So maybe you have heard of the aptitude treatment interaction theory, which says that, high performing learners, you can do whatever and they're going to be fine. By the way, I'm doing a hand wavy, theory explanation. It's more complicated than that, but basically the low performing learners are more likely to benefit from an interaction or be harmed by an intervention. So you want to look at what's the difference for the high performers and the low performers, and maybe the medium performers. And it looks like, for this explained Chunky Parsons problems, the normalized learning gain was better than the control. So we have negative learning gains because the transfer test is harder than the pretest. By the way, the post-test is harder than the pretest. All right, but we did have some positive learning gains. So again, for the medium scores, we also had normalized learning gain was better than the other two conditions, not significantly different for the high-performing learners. All right, so again, I mentioned I was going to skip this. So I was going to tell you what we presented this year about Parsons problems 2 years later. At the CS EDM workshop that was held this summer. So we wanted to see, we added more guides for the Parsons problems because basically even those results were good, they weren't great. And they were really making the students spend a lot longer on the tutor. So we really felt we needed to improve those. All right, so how do we do that? Okay, same picture as we had before, basically. But we added step-specific hints. So one thing we found was that when students were doing problem solving, they actually had access to our data-driven hints that we have built into the system. But when they had the Parsons problems, they had no hints. So we also added self-explanations to have the students tell us how doing the Parsons problem helped us. So these were not a learning intervention. The self-explanations were more for us to understand, like, hey, we made updates to Parsons problems. Do you understand them now? That was really the purpose of doing that. And we wanted to make sure we were lowering that cognitive load that we had introduced by putting Parsons problems in, but we still wanted them to engage with those that intervention. So we want them less passive than worked examples, more active in the problem solving process, but still not having to generate everything from a blank page. All right, so we already went through all of that. We've got still the pre-test, post-test structure that we had before. This is problem solving, like I mentioned before. Here's a worked example. This is the chunky Parsons problem. These blue things are not on the environment when the student sees them, like these dark blue outlines. These are just labels for y'all. But this is what the student sees. So this pop-up, this with the blue background, it actually tells them what to do next in this Parsons problem. So remember on the first example, I only showed you that only had orange question marks. Now we have yellow ones. And this is a screenshot of the student who they've done this, they've worked backwards from the goal to connect this chunk number 2 to the conclusion. And then they're getting directed, like this thing turns yellow and says, hey, you're going to derive H going backwards, click the yellow question mark, circle, and apply the simplification rule to connect it to the parent node, which is the sub goal of the previous chunk. So we're telling them exactly what to do, and they're getting to see. So now they don't have to think about what to do. What do I click on? How do I figure out how to connect these nodes? They're getting told what to do. And then they can actually focus on this as an example, like a worked example where they have to do parts of it, but they need to, they've got to pay enough attention to be able to do them. But it's kind of something in between a worked example and a problem solving. That's what the intention always was. All right, so then we studied that in spring 2024 with the guided Parsons problems, with the new sort of guide them through step-by-step, how do you solve a Parsons problem? And we looked at the impact. And we have 3 metrics, the solution length. So for programs and for math, we like short solutions. So solution length being shorter is better. Problem solving time shorter is better. And accuracy of rule application, like did you pick the right rule at the right time? Those are all important. And the score is a weighted sum of those 3 metrics in the range 0 to 1. And we looked at normalized learning gain and learning efficiency. So again, same thing, post-test minus pre-test, over 1 minus the pre-test, square root of that as normalized learning gain. And learning efficiency is that normalized learning gain divided by the tutor completion time. I'm always concerned in my research with how long is this system taking the students? And the reason why I'm really concerned about that is when I first started automatically generating hints for students, gave them to them, I found out that students were 3 times more likely to finish my tutor than they were without them. And I was like, wow, maybe the hints are, students must be giving up before they, if they don't have hints, they're giving up and they're leaving the tutor. But actually, when I went and looked at the data, I actually found out that students are spending a certain amount of time before they leave the tutor. And if they get to that time, they're done. And if you think about it as a person, right, students are taking like 5 or 6 classes. They only have so much time for each homework. When they get to that 3-4 hour mark, they're done. If they haven't finished it, that's it. It's only a homework. It's worth 2.5% of their grade. That's it. So instead of like students weren't giving up, they were like, I'm using my time efficiently. And if they got a hint, they could finish everything in the time. And if they didn't get a hint, they couldn't. So those hints are really important. But I always think learning efficiency is super important because for me, I'm like, hey, if I can learn it faster, please, system, help me learn it faster. I do want to learn it, but I also want to get it done as soon as possible. So I'm always trying to build that into systems for students. All right, so how did it work? We didn't have any difference in normalized learning gains. So students in the guided Parsons problems, because they were randomly assigned to get guided Parsons problems for some of them, and the control got some worked examples. So there weren't any differences, but we did have slightly more students who had a positive normalized learning gain. Remember, the post-test is harder than the pre. But we had much higher rule accuracy scores. So this goes back to my comment at the beginning that we think we're teaching problem solving, but what we're actually teaching is how do you apply these rules? So we more successfully taught the students the rules with a rule accuracy score of almost 80% on the post-test, with a very significant result for the Parsons problems. And these are those 4th problems in each training level. So they were also better during the learning. In the middle of the tutor, they were better. And at the end, they were also better. All right. And then we wanted to see, okay, when is this learning happening? So the control group was spending less time in the tutor. Remember that they had interleaved problem solving and worked examples, and they're not spending time on worked examples. The guided process problems still did take more time. So this is 1.52 hours as opposed to 0.81 hours. So those training levels are not spending a lot of time. Remember, they can have hints, and the control group is also getting some worked examples. So the guided process problem, they did spend more time, but more time isn't always worse. If I spend more time and I learn more, that's a win. All right, so they spent similar amount of times on the level end tests and the post test, and the total tutor time overall was about the same for the guided Parsons problems, but they spent more time in that training when they had a chance to learn things instead of spending more time struggling on later problems. But it wasn't significantly more time overall. All right, so how does that work out? It looks like they had fewer, so we have our controllers in blue, our guided Parsons problems in orange, so they had fewer incorrect steps in the level and test problems and the post-test problems. I think that's it. Those are significant. So remember that our overall score was between rule accuracy, step count, like lower is better, problem time, lower is better. So if we look the control versus, this is for looking at high learners versus low on the pretest. It looks like for rule accuracy, we did have these p-values are showing not significant. So the only thing significant is the blue with a star. So the step counts were better for the guided Parsons problem. So 9.6 steps instead of 11.1. That's a better problem solving. And it looks like also on the post test, they had a significantly lower problem time. So faster than the control group for the high learners. And then for the low pretest scores, we had much better scores on rule accuracy. And actually, step count was a little bit better for the control in this group, but these guided Parsons problem students, they learned the rules better. All right, and even though these aren't significant, these are, better problem solving times at the end that added up. So the overall results are coming mostly from those low prior learners getting a better chance to understand the rules during the tutor. All right, so our takeaway is that we really needed more scaffolding, but we have a balance between scaffolding and student autonomy. So with worked examples, the students could skip through. They had lots of autonomy, but no learning, right? And no scaffolding, like they didn't know how to read those worked examples and get something out of it. But this was beneficial for students with low prior knowledge, and the high prior knowledge got, better proofs, the shorter ones with shorter proofs and better time. All right, so we also, remember I told you that we asked them, like, what did you get out of doing these Parsons problems? So for example, we asked, like, how did the sub-goals help you derive the conclusion? And we had 326 unique explanations from 46 students in that Parsons problems group. And then we did inductive coding on their responses. And they had a few themes. So the main thing, this is the biggest one, that the Parsons problems broke down the problem into parts, which is exactly what we wanted. We wanted it broken down into puzzle pieces that weren't too confusing to put back together. And they helped them understand the rules. They reduced the difficulty because the students weren't facing that blank page anymore. They could work on simple goals and not get distracted. When they say long mistakes, you remember when we looked at those interaction networks and it was like spaghetti with super long strands? Some of those students take 20 steps to solve a problem. And these Parsons problems are showing students expert solutions. They're short. They're seeing how to solve that problem without doing a lot of extra steps. So they also got some training on backward reasoning, although this is way lower in terms of comments, and difficulty was commented that they made it easier. We did have a couple of students did say that it was disruptive to their reasoning because the problem wasn't solved the way that they expected. So if you look at the adaptive Parsons problems work by Magyar Haynes and Barb Erickson, you'll see that actually the cognitive load for adaptive Parsons problems can be high if the problem solution is very different than how they expected it would have been solved. So this is consistent with the adaptive Parsons problems work in programming. We're finding some similar things that if the student, if what we're showing to them is significantly different than how they would have solved it on their own, then they may have some trouble actually, really learning from that. All right. There are some limiting factors. Of course, we didn't give any self-explanation prompts, which we know that research on self-explanation shows that if students reflect on what just happened, they are likely to learn some more. We did not give that to the students. We could ask the students to do the same kind of explanation after every worked example to address that. And we do believe that we should do more adaptive Parsons problems where we, instead of presenting the optimal Parsons problem, we can take our data and we can present students with an example, a Parsons problem that was derived from an example that's more like what we would expect them to solve. And we have that data. So that is something that is very doable with the systems that we have. Okay, so I think I have a few more minutes. I wanted to stop right at 9:45. So I've got 2 minutes. And I'll tell you a preview. So we just got a paper accepted to Computers in Education, AI, because we wanted to see, like, how can we add LLMs to this system, which is what everyone is doing, right? So we wanted to see, can LLMs solve logic problems? And, the too long don't read is that LLMs are not so great at logic proofs, but definitely terrible if you don't give them any examples. So zero shot is terrible. Few shot is definitely needed. So we evaluated so we took student proofs, snapshots of student proofs, just like what they, in these interaction networks, we gave them to LLMs, and we rated, we said, hey, give a hint for this state that the students are in, this snapshot. We rated them for consistency, clarity, giving a justification for the hint, and whether or not it gives a larger context for subgoaling. And we compared different LLM models with different prompting strategies and different models, few shot chain of thought, plan and solve, and several others, the dual chain of thought, and that sort of thing. DeepSeek was the best, but see, these numbers aren't great, right? Like, you wouldn't say, hey, let's go to this TA who's going to give you a good hint 50% of the time. So DeepSeek's doing the best with logic, getting much closer to something that might be acceptable for a real tool. And we did some more extensive analysis. I don't have everything on here, but basically, we were finding out that when there were steps that were suggested, basically longer statements within proofs and things with more negations and more operators were causing these models to do worse. So the way that you can see that on here is we looked at correct steps that were hinted and incorrect steps that were hinted. And the parents, remember, you got to click on two parents and to derive a new node. And the length of the parents is influencing whether they got it correct or not. So if you look at all the incorrect steps that Llama 3 gave, the parents were long. And in the correct steps, the parents were shorter. And we have the same trend across all of those models. All right, so thank you so much for having me today. These are the titles and citations for the two papers that I presented today. The other one is, this one was published in CSEDM, the second one, but that was just the easiest way to get the PDF online is with this archive link. And now I'm ready for questions.
Oh, thank you so much. That was very wonderful. So I have too many questions. Maybe I will allow others to ask first and then ask you. So we have one question ready from Leonardo Silva. So in the experimental design, is the control group formed by the same subjects at all levels? I think it's a clarification question.
Yes, all of the control groups. So in all of these experiments, we randomly, so everybody takes the pretest, and we randomly assign students to conditions, but we do, in that random assignment, we make sure they're balanced between conditions as they're assigned. But as soon as the student takes the pretest, they are assigned to a condition for the rest of the tutor. So the control students, all of them are from the same discrete math class, assigned, like, while they're taking the tutor, assigned to conditions.
Oh.
So any stratification was a post hoc analysis, but we do look at that pretest to make sure that we're sending students to all the conditions, like the equal number from each condition.
Okay.
Sorry, equal number from each level, high and low.
Yeah. So if the questions are on the Q&A QR code, can one of the panelists paste it in the chat? So meanwhile, I will ask you, I have one clarification question. When you said hint, it's the hint about how to use UI and not the hint about how to solve the problem, right?
That there's two kinds of hints in our system. So I'll go back to one of the slides.
Yeah,
Sorry,
it's
just a second.
41 or something slide.
Well, I'm going to go back way early because in the first, this first place right here, if you look at the bottom here, this is a hint. So
Yeah.
this is a content hint. It's not about how to
Uh,
use the interface. So we did when we modified the Parsons problem between the first study and the second study, we added
mhm.
hints that were a combination of how to use the interface plus the content. So let me go to that slide, and I think you were right. It was somewhere around 40 something,
Yeah.
where we had that. This one right here.
Yes.
Um, this is both a content and it's telling them like click the yellow
Mm.
you know, place, and then, where it is above, not H, and apply rule simp, which is referring to a button that's on the right, which we can't see in this screenshot, to connect it to the parent node. So it's actually telling them exactly what to do and how to do it in the interface.
Yeah. Okay. Thanks. So we
Mhm.
have one more question, I guess. How do you deal with the concern that some students might be disadvantaged by their assessment to a particular group? If any intervention works, are you denying it to some students?
Um, we are that's part of what we're doing when we're looking at the interventions. We know that we look at our previous data and we see like what impact has worked examples had on students. And I showed you, that basically they're not reading, they're not even reading um, the worked examples. Like they're not spending enough time so that they could have actually learned anything from the worked examples. So that's our baseline condition
Mm.
in most of our tutor is a worked example or something we think is better. So when they're getting that intervention, so it could be seen as a disadvantage not to get Parsons problems. But when we first made them, we didn't know if they would be. We hypothesized that they would be better, but it turned out they took longer for students to learn.
Mhm.
But we're randomly assigning students to those conditions. Now, if someone came to us and they said, hey, my friend is getting these cool things and I want them, we just reassign them to conditions. So we're not forcing students to do it, but theoretically, people should learn from all the different interventions that we try. They're all data driven. They are all sort of random assignment, like randomly getting worked examples or Parsons like problem solving, and everybody gets the same number at the end. And at the end, they're all basically spending about the same amount of time and they're solving the same post-test problems. So it's during the training. So if you noticed, they're spending like 4 or 5 hours on this tutor total. And in the control group, they spent 0.81 hours in the training. And that's where those interventions are different. And the Parsons problems group spent an hour and a half in that. So they spent longer, but they learned more. So
Okay.
they could have chosen to learn more from the work examples. But you can see that actually it's the pretest and the post-test that are taking a lot longer than those training problems.
Thanks, Simon,
Those
for
are
the
great
question.
questions.
Yeah. Um, uh, to the next question I have is, uh, why did you not use any reasoning models for the LLM? So all the last set of slides, when we have any complex math problem related problem, we always use reasoning models, but all the models that you shown are like the normal models. Even 5.0 has some reasoning, but you did not use it at, I guess, right? So reasoning
Well,
model
the
always works better.
the paper was just accepted, which means we did the work like a year ago.
Okay.
But reasoning models weren't as, readily available. But we were also looking at this is a class that we teach every semester to about 300 students, and we
Uh,
need to have like a maintainable, usable, sort of like off the shelf, use it quick model. So we were using sort of the things that gave a balance of like being like we didn't have to maintain it as much, and also we could take it off the shelf and just see like what is it if we took the best things off the shelf, what could we do? But yes, there are definitely better mathematically reasoning models.
yeah.
Um, I do have a student working on that right now. She's looking at some different reasoning models, but she's not done with the research, so I can't show you the results yet.
Yeah, we wait for the results. So I have one last question, so which is twofold. One is, did you get a chance to compare CPP versus GPP? Not the control versus GPP. It's the initial set of CPP when you started in 2023 versus GPP. And the second
Yeah,
thing
we
is,
Go ahead.
Yeah, you can answer that. Then I can ask the next question. It's okay.
So we had done in the intervening study after that 2023 study. So we had some significant results there, but it was like a low number of students who were doing better with those
Uh-huh.
Parsons problems. And so we basically, when we find something that we think is terrible, we get rid of it.
Mm.
So we
Okay.
didn't do any more conditions with CPP. We only added the guides because we felt that, the students really did need that instruction on how to use that new interface for the Parsons problems. I think it would be good to, how I just said that the hints are basically combining the content with where to click.
Mhm.
I think we need to do more faded scaffolding where that goes away after a few. But right now, when we have 6 training levels, they're probably not doing more than 6 or 7 of those guided Parsons problems out of all the training that they're doing, and they do between 13 and 18 problems of training. So it's less than half of those that they're doing. It's about a third. It's anybody only ever does a third of their problems as intervention problems. So that goes back to the
Oh.
question about whether it works. And so, when are we going to scaffold it? Like after two, three problems, but they aren't getting them one after the other. Like maybe they forgot since the last time. And it might be depending on how hard a level is for somebody, it might be 30 minutes or 45 minutes before they see the next one. Just depends on how long they're taking on things. So we haven't done a detailed study to figure out like when should we reduce those scaffolds, although I think that would be a useful adaptation.
Yeah. So the second part of the question was, I have some answers in one of your slides, but um, GPP is very promising from the theory perspective. But is learning gain a better measure to say that it's more impactful? Because learning gain doesn't have that much significant difference. But even in the themes, we can easily make out that it's actually impactful. That's what we are looking for. So do we have to use some other measures to see that GPP is actually making them learn as a process becoming better?
Oh, that's a great question. We don't have a lot of time left, but I think some of the analysis that was done in the first that I skipped over, that Dr. Preya Shabrina did. She did her thesis with me, and she really looked at a lot of what was going on when students solved problems. So what she did is she analyzed students. This picture right here kind of shows it. Um, so she looked at what students were doing in their problem solving. So she just looked at their series of derived propositions, and she looked at looking at time gaps for students. So, a chunk to me, like I made the case that experts do chunks, right? And so she wanted to see, are students making chunks? And so we could do this analysis for the guided Parsons problems too. So this was done for the CPP study, not for the GPP one, but we looked to see like, are students like deriving a few things for a sub goal? That's the idea. It's like, are they doing a chunk? So looking at a gap in time where the time gap, like several things in a row have very short gaps in between them, and
Mhm.
that might be a chunk, right? And
Mhm.
or another one might be where there's a big gap between two propositions, like, okay, I knew what to do for these, and this is what my sub goal, and then there was a big gap, and then I started doing some more stuff. So these blue ones might be sub goals, and the time gap, sort of small time gap, means that they're still in a chunk, and a bigger one means like, hey, I got to figure out the next thing to do. So she did this analysis and looked to see like how many of these potential chunks from student work overlapped with those expert chunks that like when they were doing problem solving on later problems where there were no Parsons problems, did they do expert chunks, right? Because we could use the data to do expert chunks for all the problems, and we can compare the student work to see like how often did they do something in a chunk, like the way that an expert would do it. And that's the students who did you see CPP were more likely to have chunks. And I think that's part of where this came from, like these results that we hypothesized that they were actually, so most of them actually did have at least one chunking instance, and that we think that the students are learning from that. So I think one way to do an analysis for that guided Parsons problems is to look at, like, do they have evidence that they've learned how to do chunks?
Yeah, sounds good. Any other questions?
While anybody might be formulating a question, I just want to add one other answer to the whether some students might be disadvantaged. We think about that a lot, and we always do our IRB studies, IRB approval for all of our studies, and we do carefully think about the benefit for students. And if I think that something's going to make a big difference, like I didn't think Parsons problems would make a huge difference. and they're not, right? We're seeing better learning
Yeah.
learning gains
Yeah.
and slightly better time. But whenever I think there's going to be a big difference, we do what's called a switching replications, where we have like for the first half of like the tutor, for example, they would get one kind of intervention that, and then in the second half they'd get the other. And so we'd have a group like AB would be one ordering of getting interventions, and then BA for the other. And then we could see like, or students will get half and half of two different kind of interventions, but one of them gets them before the other. So then we can see if there's an ordering effect. So like a little experiment within, but everybody gets the same number of all the different kinds of interventions. That's the typical way that I usually deal with that in my research studies.
Yeah. Thanks for that. Okay. If there are no other questions, I would like to thank Timarens for this wonderful talk and very informative one. And the students who are here, please scan the QR code to provide the feedback and fill the survey form. So it will be there for 1 or 2 minutes. So if you have any other question, quick question which can be answered in within 1 minute, so please.
There's one in the Q&A. In this
Okay.
approach, you have to identify the sub-goal first, right? So actually, no, we use the graphs of the students' steps and use those rules. So those interaction networks are snapshots of steps. And then we apply edge betweenness. If you take a look at the papers, you'll see the references for those. We apply edge betweenness to partition that interaction network into clusters, and we label the last step in a cluster as a rule. So the three rules I presented in the talk are the rules to label the subgoals. We did an expert hand check to verify that they aligned with reasonable subgoals for those logic problems, but they were derived purely from data. And so if you have data where you know how many transitions, you know what steps students are doing, and you have the transitions, you could label them. But our system it is able to tell if a derived logic step is correct or not.
But what if they just use the hints to complete the task?
We have looked at the hint usage. Students, the hints they don't typically use them that much. I think we have a
Okay.
limit, like that they can't ask for more than 4 on one problem.
Uh,
But we also haven't seen too many people abusing the hints. So occasionally we'll get one student who uses a whole lot of hints, but most of the time, the majority of the students don't abuse the hints. And we've got some previous research. So if you look at Mehek Maniktala, she did a lot of research on help appropriateness, help need, and help abuse. And we did not find that there was a lot of help abuse going on.
Fantastic. Yes. Any other questions? Please fill the survey form. Please scan the QR code.
It looks like one person can't enter the link.
Okay. That question is for the Wang. So the link is not working, it seems. Can you please post the proper link on the chat?
Actually, I'm rereading this question. So while you guys are figuring out that survey link, you're asking how can we use it in a subject with no previous records? So I do have previous research that shows that you can seed the kinds of interaction networks we use with experts solutions. So if an expert solves a problem, you can use it as an initial, but there's nothing for clustering in that case. But if you have an expert solution, the expert can say like, this is a really, like I was doing these things to get this. So if you have an expert solution, they can label the subgoals. Also, you can work backwards. So if you're working backwards, we've also hypothesized that anything that you did work backwards is a subgoal, because a backward step is, I think I can derive this thing by using these rules, and you're not using the given, so you're not working forward. So when you're working backwards, you're also setting subgoals. Great. Well, thank you so much for having me. I really enjoyed it. And it was a great excuse to sort of see how the trajectory of our research has gone. Thank you so much. And thanks for the wonderful introduction. And I really appreciate the invitation from the APSCE.
Thank you so much, Tiffany. Thanks once again. Yeah, thanks for accepting
Bye.
the invitation at the last minute. Yeah, thank you. See you. Thanks,
Thank you.
everyone. Yeah, see you all.